Let's continue our talk about digital control strategy, and let's start with an interesting feature that happens only in digital environmental. It is the time delay of computing things. In analog controller, in continuous time domain controller, there is no such a time delay. What is exactly this time delay and how to do with it? Just for you to have an idea, imagine an algorithm. You take the input data, you run a lot of calculus, and then you have the final result. At the same time you have the final result, new values are already available at the inputs. Your final result has a time delay related to the current values. Let's take a better look of that. Delays in digital control strategies. In digital control strategies, some functions may cause a delay to be computed. The PWM is an example. Suppose that you have a new reference value, then you need to compute the output signal of the PWM. This computational takes some time. Another source of time delay is the control algorithm computational time, which is the time required by the microcontroller to compute a new value given the input values. You have a lot of values available at the input, your algorithm computes something, and then you have a final result as I was discussing previously. At the time you have this new value, you see that there are already new values at the input. And this, of course, is a delay in our digital control strategy. It means that the current value of our controller is being computed with past values of the inputs. Again, try to memorize this situation. You have a result of a computational calculus, but at the time you have this result, there are already new values available at the input. And these delays can be modeled and taken into account during designing a digital controller. Fortunately, we can consider such time delay in our digital control strategy, we can model it, and later our controller can be designed to compensate at least these delays. This figure shows a simplified block diagram of a digital control strategy where the delay effect of the PWM is being considered. This block diagram is for an output current control. We have the reference, we have the PI controller, and most important, and this is the point that I like to highlight, is the model that is being used to model the PWM delay. In this case, the delay effect is modeled by the PWM approximation, which is one of the most used approximation transfer functions to model PWM delay. You may find other approximation, but this is a good one. It also depends on the sampling that you are using. If you are using double PWM update or single, it depends also in other aspects. I recommend for you to take a look at this book. This book is really good for digital control in power electronics. And for me, of course, this is one of the greatest book about digital control. Take a look later at this book and you see that how to model correctly this and how this is obtained. This figure tries to answer a common discussion that really happened in our classes and research lab. It is really necessary to consider the delay of PWM or other stuff in our digital control strategy. This figure tries to answer that. I'm here with a board diagram of two curves. One is for the transfer function not considering the PWM delay, and another one considering the PWM delay as a transfer function showed previously. This is for magnitude and this is for phase. We can see that for magnitude, both curves are coincident. This is expected because a delay in time do not change the waveform of the signal, do not change the amplitude, it's just a delayed version of a signal. But in phase we can see the delay. In phase we can see that the delay represents a phase lag, and our controller of course needs to compensate such a phase delay. I'm pointing out here a region of interest because at this frequency, this is supposed to be the desired cutoff frequency, and this point is in which the controller will act in the most essence. Of course, the controller will act in the whole range of frequency, but at this point that we need to have the desired cutoff frequency and the desired margin phase. But looking at this frequency, we can clearly see that the controller must advance the phase in a much more higher value, when you are considering the PWM delay effect in your model than when you are not considering. This is the importance of considering the PWM delay, because your controller will advance the phase quite higher up to reach your desired phase margin. And a final comment here in discussing delays is that sometimes we can neglect such a delay. Of course, it depends on the application, but it's not unusual to find researches and papers that the author did not consider the PWM delay on their modeling. So we usually find that, and my final message here is when you can employ the time delay modeling, I think it's a good idea, but in most cases your system may work very well without considering the PWM delay. Of course, it's up to the designer to decide or not, and it's up to what response you may have, but delays is an important feature in digital control strategies, and sometimes we need to take a special care of that. All we have seen so far in this tutorial is theoretical, and it is an overview. After following the procedure to design a digital controller, after checking it through simulation, it is time to deploy the controller in a real microcontroller. In the next section, I'll give you an overview of some common manners to load and run the digital controller in power electronics applications. Of course, this is from my point of view and from the environment I'm familiar with, which is a lab in an university. Experimental verification. There are three major ways to employ a digital controller. The first is in a microcontroller. We can use a digital signal controller or a digital signal processor. The most common, at least from my point of view, are the F28335 and F28379D from the Texas Instruments company, and also some FPGA as possibility to employ our digital controller. Some configurations may use a combination of them, a digital signal controller and an FPGA. Another way to employ a digital controller is using the DSpace, and another one is using the hardware in the loop. Let's take a careful look at each one of them. Microcontroller. In case we employ our digital controller in a microcontroller, we need to have the microcontroller itself plus all the hardware of our power electronic application. This picture shows an example. I have here the microcontroller, and I have here all the structure of the power electronic application. Making a zoom close to this microcontroller, you can see here the control card is where our digital control strategy is running. Summarizing, using microcontroller, you need to have the microcontroller plus all the hardware. The second option is the DSpace. In this case, we also need to have the DSpace plus the hardware. The DSpace comes in replacement of the microcontroller related to the previous case. In this case, when we are using DSpace plus hardware, we need to have all the hardware, the inverter, all the hardware of our power electronic application, and the DSpace is right here. The advantage in this case over the last is that we can simulate our environment in Simulink and running the controller directly in Simulink and upload it into the DSpace. The third option is the hardware in the loop. In this case, you need to have the hardware in the loop plus an external microcontroller. This picture shows such a situation. In red here we have the hardware in the loop device, and in green we have the control card of digital controller, our microcontroller. In this case, the microcontroller is interacting with the hardware in the loop. All the power structures is running in the hardware in the loop device, and the controller is running at a microcontroller. From the point of view of the microcontroller, it is interacting with a system that the controller doesn't know if it is a real hardware or a hardware that is being emulated in a hardware in the loop device. These are the three major types of evaluating experimentally our digital controller. Let's take a general look at the programming of a digital controller in a microcontroller. For the best of my knowledge, there are two manners for programming our digital control in a microcontroller. The first one is using a programming environment
showed in this figure. I'm using here Code Composer Studio, and in this case we need to type line by line of control strategy algorithm. We need to use any language like C, assembly, or any other depending on the microcontroller, depending on the environmental you are programming it. In this case I'm using the Code Composer Studio for programming a microcontroller from the Texas Instruments F28335, and I typed here a lot of functions. Most of these files, like the header files, libraries, are freely available on the internet, on the manufacturer webpage. We can take advantage of it and use these already available files in our project. It remains to us to type our control strategy in the main file, which is actually the .c file. And the second way to program a microcontroller is using a software that has the functionality of automatic code generation. In this figure I'm showing you a Simulink file, and this is ready to make automatic code generations for also the 28335 digital signal controller. Of course, you need to install some toolbox first, and then you have a lot of functionalities added into your Simulink. In this case, I need to set the ADC ports, I need to set how many ports I'm using, some internal configurations. I can also set the PWM that I'm using, and we ought to have between these parts is what the Simulink will convert into code. I can also have here a lot of conventional, commonly used blocks in order to run some strategy. I can have here a function which is actually a C code. This, for instance, is a POL typed in C code. And within these subsystems, I have commonly used blocks like add, subtraction, product, zero the holder, and so on. And this is what I tell you, that this is really good. There are a lot of softwares doing that because this is really easier for us, which who are practical engineers. We do not want to program, if we, in our case, but we can use this feature of softwares. I know that PCs also has this functionality of automatic code generation. Typhoon Hill also has some functionalities of automatic code generation of block diagrams. Summarizing, you can program your microcontroller through typing code or through using such a functionality in our simulation software. This is really good because you can clearly see what is going on, and the Simulink does the configuration of register, the inclusion of library files, head files, and so on.
Let's go through an example. I'm going to show you the step-by-step procedure to design a digital current controller for a single-phase grid-connected inverter.
Example. In this example, we are going to see how to design digital current controllers for single-phase LCL filtered grid-connected inverter. The methodology presented in this example is based on my paper that I published in 2020. And our controllers are linear, and they are designed based on the key factor and the frequency response approach. At the end, we need to have a digital controller described as the following transfer function. This is a transfer function in the Z domain, and what we need to compute is this coefficients of these transfer functions. Depending on the order of our digital controller, some of these coefficients may be zero, and again, the controller is designed when we got all the values of this transfer function. This figure shows the power electronic application of our example. It is based on a half-bridge converter, the LCL filter, and the grid. We are measuring the output current of the inverter and also the PCC voltage, and these variables go to the digital control strategy. The methodology presented in this example is valid for half-bridge converter or full-bridge converter, and also for passive damping or active damping. Now we are with the simplified block diagram of the control strategy. We have here the inverter plus LCL filter, we have sensors. This is the digital environmental, in which we have our digital control unit. And this is the focus of our example. We are going to design 4 digital current controllers. They are the integral single lead controller, the integral double lead controller, the integral double lead with PWM delay, and also the proportional resonant controller, which is one of the most classical digital controllers for grid-connected inverters. In order to design our digital current controllers, we need to follow a step-by-step procedure, which is a systematic list. There are a lot of equations that we need to compute one by one, and in the end we go to have all the coefficients that I presented in that transfer function in the previous slides. We need first of all model the system and get the transfer functions that represents the relationship between the inverter output current and the duty cycle of the transistors. Actually, we need to have these transfer functions, which is the controllable variable of our interest and the variable that we can act into our system. And these two transfer functions represents at the top the transfer functions of our system considering the damping, the LCL passive damping, and this second one considering the active damping. We need also to model the delay of our PWM, and this transfer function shows such a model of this PWM with delay. And later we need to compute our open loop transfer function without the controller, which is basically the product of our transfer function, the modulation, the PWM in this case, and also the sensor that we are using in our system. In the next, we need to compute two things. They are the angle at the desired cutoff frequency and also the gain at the same desired cutoff frequency. First of all, describing a little bit this desired cutoff frequency. This is a choice of our design. We need to specify what we want as a cutoff frequency. The higher this frequency is, the faster your controller is. However, we cannot choose this cutoff frequency arbitrarily. We need to use some specifications. For instance, we need to consider the cutoff frequency at least 10 times lower than the switching frequency. In this case, in this example, we have 20K as switching frequency, so the desired cutoff frequency must be 2 kilohertz or lower, 10 times lower than the switching frequency. In my case, I'm using here 2 kilohertz. And this curve shows the open loop transfer function without the controller. We have here natural cutoff frequency, and this will be our desired cutoff frequency. At this point that we are desiring, that we have the cutoff frequency, we can measure the gain that must be compensated, and also the angle that the open loop transfer function is presenting. The controller will act in the whole range of frequency, but we need to specify this point because this is our bandwidth of our system, of our closed loop control system. After getting these values, we need to compute a lot of equations. Start with the integral single lead controller. The first step now is to compute the alpha, which is the angle that the controller must advance. This parameter is the desired phase margin that we want in our system. Later we compute the key factor, and then we compute some constants. At the end, we need to get this transfer function, which is our integral single lead controller. And these are the final equations to compute the coefficients of our controller. The same procedure is applied for the integral double lead controller, but some parameters are different. For instance, the key factor is computed in this way, and also we have a lot of constant. Finally, have the transfer function that describes the integral double lead digital controller, and we can compute these coefficients by these equations here. All the equations are here, and then we can get our digital controller. Notice that it is a systematic list, it is a procedure. We need to compute one by one and finally get their coefficients B1, B2, B3, A0, A1, all of them for our digital current controller for single lead and the double lead, and also considering the PWM delay. For the digital proportional resonant controller, the procedure is also based on a systematic list, and these equations show the equations required to design the proportional resonant controller. We can compute the Kp, Ki, and also the coefficients B0, B1, B2, A0, A1, and 2. After computing all these equations, we have our digital proportional resonant controller designed. This table shows the result of design of our 4 digital controllers covered in this example. They are the integral single lead controller, the double lead controller, the double lead controller considering the PWM delay effect, and the proportional resonant controller. I got all the coefficients of these controllers, and they are computed, of course, using those equations presented previously. But the message here is that this is the procedure to compute a digital current controller of course, in this application. We need to compute all the coefficients, and they are summarized in this table. Next, we can plot the board diagram of the closed loop system considering the 4 controllers, and this figure shows such a result. We have here the frequency response for magnitude and for phase, and we can see that the desired cutoff frequency, which was 2 kHz, is actually achieved. This is the bandwidth of our controller. We have a good response up to this frequency, and if you look at the frequencies in which the controller will act in case we are injecting active power, which is 50 Hz or 60 Hz depending on the grid voltage and frequency, and we see that in such a frequency we have 0 dB as magnitude and 0 degree as phase, which means that our steady state error will be considerably negligible. And this information is quite good. We need to plot our closed loop system, considering the whole system, considering the designed controller, and we can verify if our controller and if our bandwidth is satisfactory and if presents results that we are expecting. In this case, they are good, and then we can consider that the 4 controllers are considerably well designed. Let's check also if our controllers are well designed through simulation. As stated earlier, we can verify the effectiveness of our controller by plotting the reference signal and the controllable variable. And this figure shows this result for the 4 controllers that we are dealing with in our example. We have the PCC voltage in orange, we have the inverter reference current in green, and we have the inverter current in blue. We have for the integral single lead controller, the integral double lead controller, the integral double loop considering the PWM delay controller, and also the resonant controller. We can see that first of all of them is in steady state condition. They present negligible error. We see that the inverter output current is following its reference signal with negligible error before the transitory and after. Before we have 0 error, 0, 0, and after also 0 error. At this point, we have here an inversion of the current. This is a severe transitory just to check if the controller is good, but we can see that after some transitory, they again reach 0 steady state error. Of course, each controller has its behavior. We can see here that the single lead has such a behavior, the double lead has such a behavior, the double lead considering the PWM delay, then we have a much better behavior than this. The controllers are the same, but this is designed considering the PWM delay effect. This is not considering, but both of them reach the steady state condition with negligible error, and we see here a good response with not so long overshoot for the proportional resonant controller and reference following very well. Again, I suggest you to take a look at my paper where I have all the equations of this example. The simulations are freely available on my webpage. You can go there and download all the files in Simulink, MATLAB used in this design. And also I recommend you to check other materials of digital current controllers. I'm listing here some good books. Beyond that, I already stated along the tutorial, I recommend all of these books. This one is good for modeling. This is also good for digital control. This is for Discrete Time Control System by Ogat, which is a really good book, and also this book about digital signal process, which is the base of our digital control systems.
This is the end of the tutorial. Digital control for power electronics is a very big field. The goal here was to present an introduction, and of course this subject demands years of studies. I hope you had learned something, and I hope that this tutorial may contribute in your research in such a way. In case you have any question, please just let me know. Thank you very much for attending this tutorial.